Okay, so hi everybody, welcome back. What we're doing today is a continuation of our chapter 10 lecture on rotational motion. And what we did in the previous video was we covered rotational kinematics, and that is a description of how objects rotate. What we want to get to eventually is rotational dynamics. So we want to explain the causes of rotation. Why do things rotate? And in order to get there, we need to take kind of a mathematical detour to talk about the cross product of vectors, because this is something that's going to come up time and time again in rotational dynamics. Okay, so I want to remind you that there are two different ways that we can multiply two vectors. We can take the dot product of vectors, or we can take the cross product. So the difference between the two is this. The cross product of two vectors, let's say A and B, we would write this as A cross B, gives you a vector. So the result of this cross product is just another vector. Okay? On the other hand, when we have a dot product, and remember this was covered back in chapter 7, if we take A dot B, the result of that is a scalar, just a number. And so we sometimes call this the scalar product. And remember, we covered this back in chapter 7 when we first introduced the idea of work. So this has been covered already. Now we're going to look into the cross product. Okay, so let's talk about how we define the cross product of two vectors. Let's say we have two vectors A and B, and what we want to calculate is A cross B. So we're going to let vector C for this represent the cross product of A and B, so C is equal to A cross B. And the first thing we'd want to know about vector C is what direction is it pointing in. So we have vector A, we have vector B shown here in the diagram, and those two vectors will lie in some plane, and that plane here is shown in white. So the direction of vector C is perpendicular to that plane that A and B both lie in. So in other words, vector C is perpendicular to both of these two vectors A and B. So we'll show it going perpendicular to this plane in our picture. Okay, as for the magnitude of vector C is given by the magnitude of vector A times the magnitude of vector B times sine of theta, where theta is the angle between vectors A and B. So again, the notation here is theta is the angle between the two vectors we're crossing, and the vertical bars that you see here just denote that we're talking about a magnitude, okay? Now, there's an interpretation of this equation that we can sort of visualize here with our picture. The magnitude of this cross product is the area of the parallelogram whose sides are defined by the two vectors. So remember, we have vector A here shown in red, vector B here shown in blue. And if we make a little copy of vector A, shown with this red dashed line here, and another copy of vector B up here, we can form the sides of a parallelogram. The area inside of that parallelogram here is actually the cross product, or the magnitude of the cross product, again, which is given by this equation. Okay, so that's how you can sort of interpret what this equation is telling you geometrically. Okay, so that's not actually the whole story when it comes to the cross product of two vectors, because remember, we said the cross product of two vectors is perpendicular to the plane that the two vectors lie in. And if you think about it, that leaves you with two possibilities for the direction. So if we take a look at this picture here, where we have vector A and vector B that both lie in the plane of the page, well, the cross product of those two vectors has to be perpendicular to the page, so it could be coming out of the page or going into the page. There are those two possibilities. And so we have the right-hand rule to help us determine which one of those two possibilities is actually correct. That's why we use the right-hand rule. Okay, so this is how the right-hand rule works for cross products. You start by taking the fingers of your right hand and pointing them in the direction of the first vector. Then you curl the fingers of your right hand in the direction of the second vector. And then after you do that, your thumb will be pointing in the direction of the cross product. So let's actually try this out with the two vectors shown right here, okay? So we'll do A cross B. So start by pointing the fingers of your right hand in the direction of A, and then curl them in the direction of B. If you do this, you should find that your thumb is now pointing into the page. So the cross product A cross B is going into the page for these two vectors shown here. Okay, so the cross product is a little bit different than other types of multiplication you've seen before because the order of terms actually matters. So in normal multiplication of numbers, let's say 2 times 3, if I switch the order around to say 3 times 2, we get the same answer, so the order doesn't matter. But when it comes to cross products, the order does matter. So the cross product is what we call anti-commutative, and that means that if we switch the order of terms, we introduce a negative sign. So in other words, A cross B is not the same as B cross A. In fact, A cross B is the negative of B cross A, so they're not the same thing. So let's do an example. Let's consider these two vectors, A and B, that are shown on the page. What we're going to do here as an exercise is we're going to use the right-hand rule to determine the direction of A cross B, and then we'll do it again for B cross A, and we'll see that, again, they're not the same thing. They're pointing in different directions. So let's work this out. Okay, so if you haven't really dealt with the cross product and how to use the right-hand rule before, you probably just want to see this demonstrated live in person. So here we go. We have vectors A and B. And first, what we're going to do is take A cross B. So the right-hand rule says we point the fingers of our right hand in the direction of the first vector, which is A. So here we go, fingers of the right hand pointing in the direction of A. But then I have to curl the fingers of my right hand in the direction of B. Okay, so in order to do that, I'm actually gonna have to flip my hand around like this, then I can curl in the direction of B. And once I do that, my thumb is now pointing into the page. So the cross product A cross B is into the page. Okay, on the other hand, if I were to do B cross A, basically just switching the order of the terms in the cross product. Okay, so now B is my first vector. So I start by pointing the fingers of my right hand in the direction of B, and then I curl the fingers of my right hand in the direction of the second vector, which is A. So that's what that would look like. So now where's my thumb pointing? It's going out of the page. And that's what we meant earlier when we said the order of terms matters, okay? If you do A cross B, and then you switch the order of terms and do B cross A, you're gonna get a different cross product, okay? Because one is going into the page, the other is going in the opposite direction out of the page. Okay. So now that we've defined the cross product and we know how to calculate cross products, we can introduce the idea of torque. So let's get into this. So we know that if you have an object at rest, you need to apply a force to it to make it start moving. Okay, if you have a box sitting on the ground, you need to push it or pull it in some way to get it to start moving. Now, torque is the rotational analog of force. It's very similar to force, but it applies to rotation. The idea here is if we have an object that's at rest, we would need to apply a torque to it to make it start rotating. So we can think of force as the cause of translational motion, while you can think of torque as the cause of rotational motion. That's the idea. Now, torque is not quite as simple as force because it depends on a number of factors. So the torque depends on the magnitude of the force that's applied, the direction of the force that's applied, and also where on the object the force is applied. So to understand that, let's look at an example. Let's say you're trying to open a door, and the hinges of the door are here, the doorknob is over here. So one thing we could do is push on the door pretty close to the hinge with the force that we call Fa over here. Or we could do something a little bit smarter and push on the door closer to the doorknob with a force Fb. Or we could do something really stupid, which is to push into the hinges of the door like this with a force Fc. So when we compare these, I think we know intuitively that we get more torque if we apply the force here, Fb, and we'll get less torque if we apply this force, Fa, and then we'll get no torque at all if we apply this force, Fc. In other words, if you push into the hinges of the door like this, it doesn't make the door start rotating at all. So that shows that it's not just about how hard you're pushing on the door, the magnitude of the force, that certainly matters, but also what direction are you pushing in, right? If we compare Fb and Fc, pushing perpendicular to the surface of the door as opposed to parallel to it with force Fc, those result in two completely different torques, right? And then of course, where are we applying the force? That matters too, because Fb, if we apply the force further away from the hinges, gives you more torque than if we apply this force, Fa. So that's just an example of how these three factors actually matter when it comes to torque. Okay, so there's an equation for torque, and I want to introduce it to you. Torque is given by the cross product of two vectors. We have a radial vector given by r and a force vector given by F. So here's the idea behind that. You have some kind of object, let's say it's this baseball bat, and we have an axis of rotation. So for the baseball bat, you might imagine you drill a little hole right here and attach that to some kind of pivot, and that will be your axis of rotation that the bat can then rotate around. So the radial vector takes you from the axis of rotation to the point where the force is applied. So it's just a vector going from the axis of rotation to the point where the force is applied. And then of course, F is that force. And if I take the cross product of R and F, what I get is the torque. So let's think about units for a second here. R, that's going to be measured in meters, right? It's just some kind of distance between these 2 points. And F is a force measured in newtons. So therefore, the SI unit of torque is a Newton meter, a Newton times a meter. That's the unit. Now, when it comes to a torque, this is a vector quantity because, of course, when you take the cross product of two vectors, you get another vector out. So we already know how to deal with this. The direction of the torque is going to be given by the right-hand rule for cross products. And the magnitude of the torque is going to be given by, again, we take the magnitude of R times the magnitude of F times sine of the angle between them. This is just how we deal with the magnitude of a cross product. So let's take a look at some special cases then. What if R and F are pointing in the exact same direction or pointing in exact opposite directions? So in other words, the angle between them could be 0 or 180. Well, if you take sine of 0 or if you take sine of 180 degrees, you're going to get 0. So in those two cases, you're going to get no torque. On the other hand, how do you get the largest possible torque? Well, sine of 90 degrees gives you 1, which is the maximum possible value of that. So if we have a 90-degree angle, a right angle between the R and the F vectors, we get the largest possible torque. Torque is maximized in that case. Okay, so there's actually another approach to this. There's another way we can define torque that's completely equivalent. And what we'll do is we have the same picture of an R vector and an F vector. And here I'm just leaving the baseball bat out of the picture just to not clutter things up. So again, the R vector takes you from the axis of rotation to the point where the force is being applied. and the F vector is just your force, and there's some angle theta between them, which I'll show here. What we can do with the R vector is we can break it up into components. So in other words, there's a component that goes parallel to the force, and then there's another component that goes perpendicular to the force. So the way we can sort of set this up is to draw a line that just follows the direction of the force. This is called the line of action of the force. And then the component of our radial vector that goes parallel to that line is what we call R parallel. So that's shown right here. On the other hand, I can drop a little line that goes perpendicular to that, and that gives me R perpendicular. So, okay, well, R perpendicular is the opposite side on this right triangle that we just constructed. So therefore, R perpendicular should be R, the length here, times sine of theta. And notice how in the torque equation, we have R sine theta right here. So we can rewrite the torque equation to say torque is equal to R perpendicular times F. So the point of this is it's only the component of the radial vector that's perpendicular to the force vector that actually contributes to the torque. This component doesn't actually contribute to the torque. So sometimes we call R perpendicular the lever arm. That's just some terminology that you might come across from time to time. But the point is, the first equation we came up with for torque, which is RF sine theta, and the second one, which is R perpendicular times F, they're completely equivalent. They're just different ways of thinking about the same concept. Okay, so there's a question I want to ask you guys. If the line of action of a force goes through the axis of rotation, how much torque would be produced in that case? So I want you to actually draw this out, try to draw a diagram showing the line of action of a force going through the axis of rotation, and see if you can just figure out how much torque is produced by using that diagram. So pause the video, see if you can get this, and then we'll go through it together. Okay, so let's just draw some random object. It doesn't really matter what it is. And then let's put the axis of rotation somewhere on that object. So let's say this is our axis of rotation. And what we're imagining is at some other point on the object, maybe over here, we apply a force. So there's our force vector F. And then if we follow the line of action of that force, it goes right through the axis of rotation like this. Okay, so remember the definition of torque? Well, it's R cross F. And when we think about the magnitude of that torque, we can write it as R times F. So the magnitudes of those two vectors times sine of theta, where theta is the angle between them. Okay, so we drew the R vector, we drew the F vector. Now let's draw the R vector. Remember that goes from the axis of rotation to the point where the force is being applied. And in this case, they're pointing in the exact same direction. So the angle between them would be 0. So when we go to calculate the torque, we have RF sine 0. The details don't really matter here as to what R and F actually are, because when you take sine of 0, you get 0. So if you have a situation like this where the line of action of the force goes through the axis of rotation, you don't get any torque. And intuitively, if you think about this picture here, this is like when we push or pull on the hinges of the door, right? That doesn't actually make the door open. That doesn't actually produce any torque. Okay, so let's talk about how to find the direction of a torque. So we already have seen that we can use the right-hand rule to determine the direction of any kind of cross product of two vectors. And of course, the torque is just a cross product of R and F. So I'm basically just reiterating what I said earlier, but this is really important to get down, so let's go through it again. So torque is given by R cross F, and we want to determine the direction of a torque. So the first thing you'll do is you'll take your right hand and you'll point the fingers of your right hand in the direction of R. And just remember that the R vector goes from the axis of rotation to the point where the force is being applied. Then, after you do that, you're going to curl those fingers in the direction of the force vector F. And after you've done that, your thumb will now be pointing in the direction of the torque, which, by the way, this is given by the Greek letter tau. So tau is for torque. Okay, so this is a picture of what that looks like. So you take the fingers of the right hand, you point them in the direction of R like this. But you then curl them in the direction of the F vector like this. And after you do that, your thumb will be pointing in the direction of the tau or the torque vector. And that's how you use the right hand rule. Now, there's an interpretation of this that makes intuitive sense. This is how you interpret the direction of that torque. What does it mean when my thumb is pointing in a certain direction? So when your thumb on your right hand points in the direction of the torque, the fingers of your right hand are going to be curling in the direction of the rotation that torque would tend to induce. So in other words, let's say this is your torque, right? Your fingers are curling this way. This is indicating the direction of the rotation that this torque would tend to give you. That's kind of the intuitive interpretation of which way your torque vector is pointing. Okay, so let's get a little bit of practice with these ideas by doing an example problem. So we have a simple pendulum that consists of a mass connected to a string. So here's the mass. That's the string it's connected to, attached to the ceiling here. For each position of the pendulum shown below, determine whether the net torque on the mass is in the plus z direction, the minus z direction, or 0. So this is the coordinate system we're using. X is going to the right, y is going up like this, and then the z direction is coming out of the page towards you. So with the pendulum in position 1, what direction is the net torque? Just say positive z, negative z, or is it just 0? And then do the same for these two positions shown here. So pause the video, see if you can work this out, and then we'll go through it together. Okay. For this example, I figured it would be best to do this on the board so I can actually show you how the right-hand rule works in these examples. So let's start with the first case where we have the pendulum off to the left. So this is the point of attachment where the string is attached to the ceiling. This is the string, and then this is the mass. So the first thing we should do is just account for the different forces that are acting on the mass. One force is gravity, pointing straight down, Fg. But we also have a tension force along the length of the string, pulling it this way. So that'll be Ft. Now, as the pendulum swings back and forth, it's rotating around this point. In other words, this is the axis of rotation up here. So what we can do is draw the R vector, which goes from the axis to the point where the force is applied. So this would be the R vector. So the way this works is if we want to know what the net torque is, that would be the sum of two terms. We'd have the torque due to the tension force, and we'd have the torque due to gravity. Now, in general, how does torque work? The torque vector is given by R cross F. Okay, and if we want the magnitude, that would be given by RF sine of theta, where theta is the angle between R and F. If we want the direction, we would just use the right-hand rule. So right-hand rule. Okay, so the thing about the tension, okay, is that the angle between the tension and the R vector is 180. Okay, and if you take sine of 180, as we said before, you get 0. In other words, the tension is not causing any torque. On the other hand, gravity, that will be inducing a torque. And if we want to see how that works, we'd have to use the right-hand rule. So basically, here's the idea. Where we see the net torque is the sum of the torque due to tension plus the torque due to gravity. Just cross off the torque due to tension. Only thing that matters is gravity here. So if the pendulum is over here on the left side, so this would be case 1, right? The r vector goes this way. So we'd have to point. Okay. So if we're going to do the right-hand rule, I'd point the fingers of my right hand in the direction of r, and then I'd curl them in the direction of the force of gravity, so just straight down. So my thumb is going out of the page. Okay? So the torque is out of the page, which is in the positive z direction. Okay. Let's look at the second case. In this case, the pendulum is off to the right side. Or actually, no, in the second case, the pendulum is just hanging straight down, right? Okay. So in the second case, where the pendulum is hanging straight down, now this is the r vector pointing straight from the axis to where the pendulum is. And this is the force of gravity pointing straight down. So now for gravity, the angle between the r and f vectors is 0. So that means we're not going to have any torque at all. Okay. Finally, in the third case, this is where the pendulum mass is off to the right, like this. Okay, this is the r vector. This is the force of gravity. And again, we can use the right-hand rule to figure out what direction the torque is in. Okay, so remember, you point the fingers of your right hand in the direction of r, and you curl them in the direction of f. So now your thumb should be pointing into the page. So the net torque is into the page, which would be the minus z direction. Okay, and again, what does it mean for the torque to be in the minus z direction? Well, if I point my thumb into the page in the minus z direction, the fingers of my right hand are naturally going to be curling this way. In other words, the type of rotation that's going to be induced is this way, in the clockwise direction. That's how we interpret the direction of the torque. So here's another example to practice with. What I want you to do is find the torque, that is the magnitude and the direction, induced by the force that's shown on the diagram below. So we have a baseball bat. This is the pivot point. This is the axis of rotation right here. We apply a force to the bat going to the right at this point right here. And the distance between those 2 points is given, the amount of force is given, and the angle here is also given. We're going to use the same coordinates as before. We have x and y in the plane of the page, and then plus z is coming out of the page. So find the magnitude of this torque and the direction of this torque. See what you get? Pause the video and come back to it when you have your answer. Okay, so remember, torque is a vector which is given by r cross f. The magnitude of that vector is given by rf sine of theta, and the direction is given by the right-hand rule. So let's start with the direction, okay? We know what the force vector is. That's the one that's pointing to the right over here. Remember, the r vector, which we can indicate on the diagram, is going straight from the axis of rotation, the pivot point, to the point where the force is applied. So this would be the r vector right here. And what's the direction of the torque given that we're doing r cross f? Well, try this out. Point the fingers of your right hand in the direction of the r vector. Then curl the fingers of your right hand in the direction of f. And you should find that your thumb is now pointing into the page. So that would be the minus z direction. So the magnitude, if we calculate that, so r, the magnitude of r shown here, represents the distance between the pivot point and the point where the force is applied. So that's 32 centimeters or 0.320 meters. F, that's the magnitude of the force, which is 25 newtons. And then we have the sine of the angle between them, which is sine of 35 degrees. If you calculate this, you're going to get 4.589, but we'll keep 3 sig figs. Newtons times meters is the unit. So what we'd say about this torque is, the torque is minus 4.59 Newton meters k hat to indicate that we're in the negative z direction. Okay, let's do one more example where we just calculate a torque. As we'll see, the net torque, so the sum of all the different torques acting on an object, governs the rotation of that object. So the rotor in the diagram below has an inner radius of 10 centimeters and the outer radius is 25 centimeters. So here, 10 centimeters here, 25 centimeters for the outer radius. It is fixed to an axle, which is shown here, that goes through the center. A set of 4 constant forces acts on the rotor. Let's calculate the net torque, the magnitude and direction acting on this rotor. So let's work this out. Okay, so this is the situation we have. We have the XY coordinate system in the plane of the page, which means the Z direction is coming out of the page towards you. So that's the Z direction. And we're going to calculate a bunch of torques. For each torque, we know that the torque is given by R cross F. We know that the magnitude is going to be given by RF sine theta. The direction is going to be given by the right-hand rule. And here's the thing. All of these torques that we're looking at here, they're either going to be in the positive z direction or the negative z direction. So really, all we're trying to do here is distinguish between whether the torque is in the plus z or minus z direction. Okay? So when we calculate the net torque, which we can write this way, the sum of the torques, let's just focus on the z direction. And here's what we'll do. We'll have to add 4 different torques together because they're 4 different forces. And why don't we start up here at the top of the rotor and then just work our way around going this way, going clockwise. Okay? So starting with this force that I circled up here, the 25 newtons, the R vector is going to go from the axis of rotation to the top of the rotor where the force is being applied. So if you do the right-hand rule, again, you point the fingers of your right hand in the direction of R, so point them straight up. Then you curl them in the direction of the force, which is to the left. Your thumb should now be pointing out of the page, which is the positive z direction. So for that first torque, we have a positive sign. Then, next to that positive sign, we're going to write RF sine theta. The radius, the outer radius, is 25 centimeters or 0.25 meters. So this is R. The force is 25 newtons. So this is F. And then we have sine of the angle between them. Well, what's shown here is that we have a right angle or 90 degrees. Okay, now let's do the next one. So now we're looking at this force here, that's 12.5 newtons. I want you to notice something about this force. If we follow the line of action back to the axis of rotation, we see it's going right through the axis of rotation. So this gives us no torque. So I'll just add 0. Now, if we go to the next one, which would be over here, okay, now the r vector, if I can draw it, is just pointing straight to the left like this. So it's going from the axis of rotation to where the force is applied. So by the right-hand rule, if you want to know what direction this torque is in, point your fingers in the direction of r, which is going straight to the left, curl them in the direction of the force, which is going straight down, and you should find that your thumb is pointing out of the page or in the positive z direction. So what's r in this case? That's the smaller radius, 10 centimeters or 0.1 meters. What's f? That's 15.5 newtons, just shown on the diagram. And what's the angle between r and f? It's 90 degrees once again. Okay, now we have to do this one, the last torque. So let's start by showing the r vector. Again, it goes from the axis of rotation to the point where the force is applied. So this is the r vector going straight to the left once again. So let's do the right-hand rule to figure out what direction that torque is going to be in. So here's what you have to do. Point the fingers on your right hand to the left in the direction of r. Now you have to curl them in the direction of the force, which is kind of going up and to the right like this. So the only way you can do that is if you turn your hand over with your thumb pointing down, and you'll see that the torque is in the negative z direction or into the page. Okay, so there's a negative sign for that torque. Okay, now, the radius, now we're using the outer radius once again. So that would be 25 centimeters or 0.25 meters. The amount of force is 18.5 newtons. And now the angle between the force and the r vector is 37.5 degrees. That's just straight from the diagram. So we add all this together, and you'll find it comes out positive 4.984 newtons times meters. Keep 3 sig figs on that. So the net torque is equal to positive 4.98 Newton meters k hat. So the net torque, in other words, is out of the page, which is the plus z direction. So that's how you do that. Okay, so now that we've established what torque is, we're ready to move on to the next topic, which is moment of inertia and the rotational version of Newton's second law. So we're all familiar with the equation F equals ma. It turns out there is a very similar equation that applies to rotating objects that I want to show you here. So remember, Newton's second law, as we've come to understand it, says that the net external force acting on an object is equal to the mass of that object times the acceleration of the object. And in particular, we're talking about the acceleration of the center of mass of the object, as we learned back in chapter 9. So this equation is what governs the translational motion of an object. So the idea is, if you know the outside forces acting on your object, you can calculate its acceleration. If you know all the forces, you can calculate A. Now, the rotational version of this, that applies to rotating objects, looks like this. On the left side of the equation, we have the net external torque acting on the object. So we have torque instead of force on this side. Now, on the other side of the equation, we have I times alpha. Now, alpha is something that we've seen before. This is what we call the angular acceleration of the object, which again, we typically measure in radians per second squared. The important thing when you see this equation is that the angles are measured in radians for alpha, but I is something we haven't seen before. So capital I is something called the moment of inertia of the object, and we're going to get to what that is about, but for now, it's just sort of analogous to mass. Okay, it's kind of like mass, but for a rotating object. Okay, so let's try to understand this new equation by looking at it side by side with F equals ma. So what you see here is a table. In this column on the left, we look at rotational motion. In this column on the right, we look at translational motion. Okay, so what's the governing equation for rotation? Well, it's what we just learned about. The net external torque acting on an object is equal to I times alpha, the moment of inertia times angular acceleration. Now, if we look at the governing equation for translation, it looks really similar. On the left side, we have the net external force acting on the object. That equals the mass times the acceleration of our object. Okay, so what is the cause of motion in each of these equations? Well, the cause of motion when it comes to the rotation of an object would be outside torques. External torques are what cause things to start rotating. On the other hand, if we're thinking about translation, the cause of motion would be external forces. It's outside forces you need to get something to start translating. Now, what we have here is resistance to motion. So if we go to the translational case, that would be mass. Okay, so the more mass something has, the more difficult it is to change its motion. But now when it comes to rotation, we have something called the moment of inertia. So we don't have m in the equation, we have I, which stands in for the moment of inertia. And we're going to get into more about that later. And then what's the effect? If you exert a torque on something, what's the effect of that? Well, you get angular acceleration. You cause the object to start accelerating in terms of its rotation. When it comes to translation, if you exert a force on something, what's the effect of that? You cause it to start accelerating. Okay, so I hope you can see the similarities between these two equations and appreciate how they're related. By the way, eventually in this lecture, we're going to start thinking about objects that are translating and rotating at the same time. So think about a bowling ball that you roll down the lane. Okay, that would be translating and rotating at the same time. And guess what? We're going to use both of these equations together when we get to that. Okay, so now let's talk about moment of inertia for a while. So when we define moment of inertia, I want you to think of it as being very, very similar to mass, okay? Because if you think back to what mass is the resistance of an object to being accelerated in terms of translation, okay? So with F is equal to ma, you can rearrange that equation to say m is equal to F over a. In other words, the more mass something has, the bigger m is, the more force it's going to take to get it to accelerate at a certain rate. So you can think of mass as resistance to being accelerated in terms of an object's translation. So moment of inertia is a really similar idea, except now we want to think of this as the resistance to being accelerated in the rotational sense. So remember, torque is equal to I times alpha. That's the rotational version of Newton's second law. If you rearrange that, you can get it to say I is equal to torque divided by alpha. So what does the moment of inertia mean then? Well, the more moment of inertia something has, the bigger the value of I, the more torque that it's going to take to get it to start rotating, to get it to undergo some angular acceleration, okay? Now, mass and moment of inertia are different because if you think about the mass of an object's mass is just its mass. There's nothing else to say. If an object is 2 kilograms, that's pretty much the end of the story. But when it comes to an object's moment of inertia, that actually depends on how the mass is distributed around the axis of rotation. So moment of inertia is not some kind of intrinsic property of an object. It actually depends on which axis you rotate it about. And this is easy to see if you take a look at this example here. So let's say you have a really long but kind of thin cylinder like this, okay? Now, if you rotate it about this axis, the long axis, that's pretty easy to do, right? So if you can find an object like this in your house, just try rotating it this way, as you see on the left, and you'll find that's very easy. So it has a low moment of inertia. On the other hand, if you rotate it about this axis, okay, that's a lot harder to do. So it's the same object, but it has two different moments of inertia depending on which axis you try to rotate it about. So moment of inertia is like mass in the sense that it's resistance to being accelerated, but it's a little more complicated than that. Okay, so here's how we're going to deal with moment of inertia. We're going to start by deriving a formula for the moment of inertia of a single particle, and then we'll develop from there how we can calculate the moment of inertia of solid objects like spheres and cylinders and things like this. So for now, we're just going to think about a single particle. So we have a point particle that has a mass of m connected to a rod with a length of r. So that's the mass, and that's the rod right there. The length of that rod is r. We're going to imagine that the rod itself is massless, so it's not going to contribute to the moment of inertia. It's only going to be the particle that we have to think about. And we're also going to imagine that the particle is being rotated about an axis that goes through the end of the rod. So this is the axis here, and the axis is also perpendicular to the rod itself. So we're rotating it as shown in the diagram here. Okay, so that's the situation. Now we're going to derive a formula for the moment of inertia of this object, and we'll see how this works out. Okay, so this is the picture of the rotating object that we're looking at, and I want to draw a different picture where we look at it from the top-down view. So this is going to be the top-down view looking into the axis of rotation. Okay? So now we'll see the axis of rotation here. Let's draw a coordinate system, x, y, so that the axis of rotation is at the origin. And then our mass is going to be somewhere over here. So there's the mass, and it's a distance r away from the axis. So let's actually draw that. This will be our vector r. So that goes from the axis of rotation to where the mass is. Okay, so now let's imagine that there's some kind of force acting on the particle, okay? I'll just draw some random force vector F like this. And with that force, what we can do is we can break it up into components. So here's how I'm going to do that. Okay, this component that's going parallel to the r vector, I'm going to call it FR. Technically, we would call that the radial component of the force, okay? In this other component, I'll call that FT because it's the tangential component. So here, let's write that out. This is tangential, and this is radial. And there's some angle here. There's a right angle between FT and FR, and that's the force broken down into components. Okay, well, we have a right triangle here, so we can do a little bit of trigonometry. Sine of the angle theta that you see in the triangle we just constructed is opposite over hypotenuse. That's the definition, of course. So what's the opposite side? That's FT. What's the hypotenuse? That would just be the overall magnitude of the force, which I'll just call F. So the point of saying this all is that Ft is equal to the magnitude of the force F times sine of the angle theta. Okay, so here's what we can do next. We can apply Newton's second law, just the normal F equals ma version of Newton's second law. in the tangential direction. So remember, we're always free to break Newton's second law into components and just look at a certain direction. So we're going to do this for the tangential direction. So here, what's the force in the tangential direction? That's what we call Ft. That should be equal to ma. But in particular, we're talking about the acceleration in the tangential direction. Okay, well, that should sound familiar. Tangential acceleration. From the previous lecture, we found that the tangential acceleration of a rotating object is equal to alpha times r. So we're going to use that here. And Ft, as we said earlier, was f sine theta. So here's our equation now. We have f sine theta is equal to m times alpha times r. So what I'm going to do next is multiply by another factor of r on both sides, just because I can. So here, I'm going to have r f sine theta on this side, and I'm going to have m and then r squared now, because I multiplied by r on both sides, multiplying alpha. Okay, so remember Newton's second law for rotation. Looks like this. We have the torque equaling the moment of inertia times alpha. Well, interestingly, on the left side of the equation we wrote down here, rf sine theta, remember that's torque. Alpha, that's our angular acceleration. So guess what? mr squared right there, that is the moment of inertia. Of a particle. Okay, so this only works if you're talking about a point particle with no size. But what we get is I is equal to mr squared for a particle. Okay, that's where it comes from. Okay, so here's the formula that we derived. The particle's moment of inertia is given by I is equal to m times r squared. So it depends on the mass of the particle, and it depends on r, which is how far from the axis of rotation your particle is located. Now, what are the SI units for this new quantity called moment of inertia? Well, for mass, we measure that in kilograms. And for r, that's just some distance, so that would be measured in meters. So the SI unit of moment of inertia is kilograms times meters squared. And this equation should make intuitive sense if you think about it, right? As the mass gets further away from the axis of rotation, if we increase r, the moment of inertia is also increasing. That's what this formula is saying. And again, that should make intuitive sense because if you're holding something out far away from your body, it's hard to rotate it. But if you take that same object and you hold it closer to your body, it becomes easier to rotate it around. So actually, let me show you what that looks like. Okay, so again, it should make intuitive sense that as the distance from the axis of rotation increases, the moment of inertia of your object also increases. So here, just take some somewhat heavy object, anything you can find in your room, and just hold it as far away from you as you can. And then just kind of swing your arm around like this, and just feel how difficult that is, how much resistance you're feeling. Then do the same thing, but just hold it really close to your body. Much easier to do, right? That's because there's a much larger moment of inertia the further I hold the object out from the axis of rotation than if I hold it closer. Okay, and that's what the formula we just derived is more or less telling us. All right, So we've seen how to calculate the moment of inertia of a particle, but most of the time what we really want to do is calculate the moment of inertia of some kind of solid object that's made up of many, many particles. So here's how we're going to handle this. Let's say we have a collection of n particles, whatever n happens to be. The total moment of inertia of those particles would just be given by a sum, right? Each one would be m times r squared. So if I just add up m times r squared for all of the particles, then I will get the total moment of inertia. So the way we write this as a sum is I take the sum from I is equal to 1 to n of m sub I, r sub I. So we just need to know the mass and the distance from the axis of each particle. Now, realistically, if we had a solid object, like the water bottle I was holding earlier, we wouldn't really calculate the sum over every single atom. Instead, we would make this more manageable by turning this sum into an integral. So here's the idea. We're going to take the solid object, whatever that happens to be, and divide it into tiny little mass elements, which we'll call delta m. So here, this is some weird shaped object, but I can break it into little pieces. This is my little mass element, delta m. And notice how it's a certain distance away from the axis of rotation. So I would have a sum of, well, delta m times r squared to calculate, right? So in other words, I would want to include all the little mass elements to get the total moment of inertia. That's what's being shown here. But if I take the limit as delta m goes to 0, then I'm turning this sum into an integral. Okay, so in the limit where delta m goes to 0 of this sum, which is r squared times delta m, now I have the integral r squared dm. Okay, so this is going to be somewhat similar to what we did when we calculated center of mass of a solid object. And so the limits of integration, which are not shown here, they're going to depend on the situation, okay? They're always going to correspond to the edges of the object. So in other words, your limits will just cover the extent of the whole object. That's how you know how to set the limits. Okay. Now, with that said, sometimes these integrals can get a little tricky, so let's take a look at a couple examples. In this first example, we're going to calculate the moment of inertia of a uniform rod of mass m and length L, and it's being rotated about the center of mass as shown here. So again, the total length from this end to this end is L. The total mass is capital M. So we want to use this integral. Moment of inertia is r squared times dm. We want to see how to set it up and how to calculate it. And what we're going to get is a formula for the moment of inertia of this object. Okay, that's what we're going to do. Okay, so what we're going to look at is how I can compute the integral r squared dm to get the moment of inertia of this object. So the first thing you should be thinking is, what's dm? What is my little mass element that I'm going to use, and how am I going to break this object down into little mass elements? So the first thing we'll need is some kind of coordinate system, just to keep track of where things are. So for our purposes, it's enough just to say we have an x-axis that goes along the length of the rod. How about we put x equals 0 right at the axis of rotation here, so that will be x equals 0. And that means the right end of the rod is going to be x equals plus L over 2. And then the left end over here would be x equals minus L over 2. So those would be the limits of integration eventually, so that we cover the entire rod. Okay, so let's take a little section of the rod here. And let's say that's our mass element, dm, right there. Well, one thing we need to know about this mass element is, what's the thickness? How wide is it? Let's call it dx, because that's a little distance along the x-axis that our mass element spans. And then if we want to locate where the mass element is, well, we just need to know its x-coordinate. So this would be its x-coordinate. Again, since x equals 0 is at the axis of rotation, what I'm showing you here is the x-coordinate of that mass element. Okay, so right away, r is just equal to x, right? Because r is the distance from the axis. So distance of the mass element from the axis of rotation. Mass element from axis of rotation. That's given by x here. And now let's think about how to write an expression for dm. In other words, I want to write an expression for dm, the amount of mass that's contained in that little segment, in terms of x, okay? Because I want x to be the variable that we eventually integrate over. All right, so one way we can get this is to use the fact that the mass is uniformly distributed on the rod, or across the beam, right? Okay, so that means that we can set up a little ratio. The mass element, okay, divided by the total mass should equal the length element divided by the total length. So let me give you some intuition for why this is true. Let's say my mass element is half the length of the rod, right? Well, since the mass is uniformly distributed, then it should be half the mass also, right? If my mass element is 1% of the total length, it should also be 1% of the total mass. And that idea is encapsulated here. In other words, whatever fraction the mass takes up, that's the same fraction of the total length that the mass element takes up. Okay, so let's try to put that not in words, but in terms of variables. The mass element is dm. The total mass is capital M. The little length element is what we labeled as dx on the diagram. And the total length is L. So therefore, dm is equal to, we have big M over L times dx. Okay? So now let's put that in the integral. Remember, let's go back to the top, is equal to the integral of r squared dm. Well, in this case, r is just going to be x. So now we have x squared. And then dm is going to be m over L times dx. Okay. Before we go any further, let's pull out constants. The total mass and the total length are constants, so they can come out of the integral. And then inside, we're left with x squared dx. And at this point, let's put the limits of integration. Remember, the limits correspond to the edges of the object. So we better be going from minus L over 2 to plus L over 2. That way we can cover the entire rod. Okay, now that we're at this step, it's really not so bad because we have the constants out front, and then x squared integrates to a third x cubed. And again, we're taking that from minus L over 2 to positive L over 2. So we have m divided by 3L. Let's just pull the 3 out to the front also. And then when I plug in the top limit, which is positive L over 2, and then cube that, I have to subtract from that the bottom limit, which is minus L over 2, and then cube that as well. Okay, so I have m over 3L. With my top limit, I get L cubed, and then 2 cubed is 8 on the bottom. Okay, So I have minus, but I also have another negative sign. So this is going to be plus L cubed over 8 for the other term. All right, so in other words, I have m over 3L, L cubed over 4 is how I could simplify that by adding L cubed over 8 to L cubed over 8. And so overall, I have a factor of 1/12 m times L squared. So this is the formula for the moment of inertia of a beam that's being rotated about its own center of mass like this. It only depends on the mass and the length. That's how it works. Okay, and so there's the result. By doing this integral, we worked out that the moment of inertia is 1/12 mL squared. Let's do another example. Let's find the moment of inertia of a thin ring of mass m and radius r, rotated about an axis that goes through its center of mass and is perpendicular to the plane of the ring. Okay, so if this is the ring, this is our axis of rotation going through the center, and again, being perpendicular to the plane of the ring. So we're going to rotate it this way. We want to know what the moment of inertia is in this case. So once again, I'll show you how to set up this integral, how to calculate it, and we'll see what the result is. Okay, so for this one, I want to draw the same diagram, but from a different perspective. So let's imagine we're looking from the top down. So your eye is here, you're looking down into the axis of rotation. What would you see? So looking down into axis of rotation. So now you would see the ring face on like this, and the axis would be in the very center. That's the axis. And so as always, what we want to do is break this object, this ring, into little mass elements. So the way I'm going to break it into mass elements is to take a little section, a little slice of the ring, like this. And of course, the radius is r. But the angle that this mass element spans, this angle right here, I'm going to call that d phi. And of course, this is our mass element dm. So the mass element dm spans an angle d phi. So this is how I'll set things up to do the integral. By the way, the integral we're doing is r squared dm. So as far as my mass element goes, little r, that represents the distance from the axis of rotation. Okay, that's what it means in this formula. But the nice thing about having a ring is that every single mass element is the same distance away from the axis, right? Because it lies on a circle, this is just the radius of the circle. So again, if I just write little r equals big R, you might not immediately see what that means, but what I'm saying is the distance from the axis of rotation of every mass element is just the radius of the ring. That's what I'm trying to get across here. And of course, that means this is just some constant. Okay, so next, what about dm? How do I express how much mass is contained in that little slice? Well, just like before, the mass is uniformly distributed on the ring. Okay, and so what that means is the mass element divided by the total mass is equal to the angle element divided by the total angle. So again, the idea here is, let's say my mass element takes up a quarter of the total angle, a quarter of the circle. Well, then it's going to take up a quarter of the mass, right? whatever fraction of the angle it takes up that same fraction of the mass. So we can put this in terms of variables as dm, that's my mass element, divided by big M, that's my total mass, equals d phi, that's my angle element, remember, divided by, what's the total angle? That would be 2 pi to go all the way around the circle. So therefore, when I set up the integral, which again is I is equal to r squared times dm. So big R, the radius of the ring, goes in for that. And then for dm, I forgot to write this, but dm is equal to m over 2 pi times d phi, according to what we just did. So make that substitution. We have big M over 2 pi times d phi. Okay, so let's pull out any constants that we might have. We're going to have mass. Now, big R is a constant. That's the radius of the ring. And then 2 pi. So actually, this is not really that bad. The only thing we're left with in the integral is d phi. So how do I indicate that I'm going to cover the entire ring? Well, I should take this from 0 to 2 pi. Those would be my limits. Okay, well, this integral is pretty trivial. This just works out to 2 pi. And so what we're left with is mr squared over 2 pi times 2 pi, so cancel those out. It's just mr squared. So the moment of inertia of this ring is equal to its mass times its radius squared. Okay, so again, by performing the integral, we found that the moment of inertia of this object is equal to the mass of the ring times the radius of the ring squared. And so I'm just going to put this table here for you to reference if you need it. There's actually a very similar table in the textbook. That would be figure 1020 in the textbook. And basically, it's just a list of common moments of inertia. Okay, so we have, just to pick out a few, the rod rotated about its center. That's what we worked out as 1/12 ml squared. We already saw that. Thin ring or a hollow cylinder rotating about its axis, mr squared. That's one we worked out. There are a whole bunch of others in this table. Things like spheres, planes, cylinders. And what I'll say about this is you should know how to calculate pretty much any one of these. So on the homework, I'm going to ask you to do some problems where you calculate the moments of inertia of some of these objects, okay? But if the problem isn't specifically about calculating a moment of inertia, it's about something else, you can go ahead and just grab the relevant formula from the table. So in other words, I'm not expecting you to do this integral in every single problem you see, but there will be some problems that I give you that are specifically about calculating a moment of inertia, and in those cases, you should know how to do the integral. Okay, so the last topic that I wanted to touch on in this lecture video is the parallel axis theorem. Now, for this, I'm not going to show you the derivation. There's a derivation of this in the textbook. I just want to quote the result to you and then show you how you can apply this idea. So here's what the parallel axis theorem says. Suppose a rigid body of mass m has a moment of inertia, ICM, about an axis which goes through its center of mass. So in other words, if we take the object, whatever it happens to be, and we rotate it about an axis that goes through the center of mass, this would be ICM. That would be the corresponding moment of inertia. So now, let's say the body rotates about a new axis, which is parallel to the first one, but it's displaced by some distance d. So remember, the first axis goes through the center of mass like this. The new axis is offset from that, but it's parallel to it. So that's why we call this the parallel axis theorem. And it's offset by a distance which we'll call d. So that's the distance between the old axis and the new axis shown in the diagram. Okay, If that's the case, if that's the situation we're dealing with, then the new moment of inertia is going to be given by I. That's the new moment of inertia is equal to ICM, the moment of inertia about the axis that goes to the center of mass, and then plus m times d squared, where again, m is the total mass of the object, and then d is how much we've offset the new axis from the old one. Okay, so before we end this, I just want to do one example where we put this idea to use. So let's see how we can apply the parallel axis theorem. So this question says, find the moment of inertia of a uniform rod, mass m and length L, rotated about its end, as shown below. Okay, so we can use the parallel axis theorem because we've already worked out what the moment of inertia would be if you rotate it about the center of mass. So we're basically shifting the axis over to the end of the rod, and this is a perfect example of where we can use the parallel axis theorem. So let's work it out. Okay, so here's the situation. We already calculated ICM for this object. In other words, we calculated that if you rotate a rod about its center of mass, then the moment of inertia is 1/12 ml squared. So that would be, again, this axis here, which goes through the center of mass, which I'll show with an X right here. So the new axis is now at the end of the rod. So the distance between, here, this is the old CM axis, and this is the new axis at the end of the rod. The distance between those two is half the length of the rod, L over 2. So if we apply the parallel axis theorem, I is going to be ICM, which is 1/12 ml squared, plus m times the distance, L over 2 squared. Okay, so we have a common factor of ml squared in both of these terms. The first one is 1/12. The second is 1/2 squared, which is 1/4. So let's just work with the fractions to simplify this. We have ml squared, and then we have, so 1/12, and then 1/4 is the same as 3/12. So we've got ml squared. Put these two terms together, we have 4/12, and that simplifies to 1/3. Okay, so 1/3 ml squared, that is the new moment of inertia. Now notice how this is larger than before. And that should make intuitive sense, because it's easier to rotate the object about its center, okay? It's easier to rotate about this old axis compared to this new axis. So the new axis will have a higher moment of inertia. And again, just take any kind of object that you see lying around that has this shape. If you try to rotate it about the center, and then you try again to rotate it about the end, it's much easier to rotate it about the center. So that's going to be it for this video. In the next one, we'll take this idea even further. And so until then, be safe, be healthy out there. I'll see you in the next one.